So to evaluate such integrals, then numerical integration is required. The principal tools in evaluating definite integrals with equally spaced points are those of the Newton-Cotes formulae. Lagrange interpolation from the first online lecture is used to attempt to evaluate the integrand between a number of points and then integrate the resulting interpolation function. So just to remind you of the Lagrange interpolation method, for a linear function, which is linear, also turns out to be linear interpolation, we have 2 points, x0 and x1. We use the first of these points, x0, as the first anchor, and then divide this by x0 minus x1, and then we simply relax the x0, so x0 minus x1 on the top. Move to the next anchor point is at x1, so on the bottom we have x1 minus x0, and on the top we have x minus x0 as the x1 is relaxed. You could then perform the integration. This is relatively straightforward with a substitution of, say, u x minus 1 and v x minus 0, and changing the dx accordingly. When this is performed, you should find that this is f1 plus f0, where f1 is the value evaluated at x1 and f0 is the value evaluated at the value of the integrand evaluated at f0, divided by 2, x1 minus x0, and if we note that x1 minus x0 is simply the length of the strip h, the width of the strip h, then this is a trapezoid, as expected. If you don't want to go through the integration process, then the commands in SymPy are here. So this is to find the integral of x minus x1 divided by x0 minus x1 multiplied by function f0, which essentially is a SymPy representation of this first integral, or this first integrand, and then the second integrand is x minus x0 divided by x1 minus x0 function at 1. And then the next is a tuple, x, x0, x1, and I've asked the SymPy to actually do the integration using the do-it method. Thereafter, just simply factorize the integral p1 or ip1, which we've called here, and the result will form out. Moving on to the say a second order Lagrange interpolation, the procedure is very similar. First of all, we evaluate the function at f0, and then we use the distances from x0, so x0 minus x1, x0 minus x2, and above we then relax the x0 to have x minus x1, x minus x2. Moving on to the next point, which this time would be at x1. So x1 is our anchor point, x1 minus x0, x1 minus x2, and then simply relax the x1 to get x1, x minus x0, x minus x2. On to the next point, evaluate the function at x2, divide by x2 minus x0, x2 minus x1, and relax the x2's to find x minus x0 and x minus x1. Again, this is a little bit more tricky, as you probably need to do either a double substitution for each of the integrals, or alternatively expand these terms and then collect terms. So I've just used SymPy, and I've used the nomenclature L0, L1 and L2 to show the values of the Lagrange, they signify the Lagrange evaluated at x0, the Lagrange coefficient evaluated at x1, and the Lagrange coefficient evaluated at x2, L0, L1, and simply multiplied, simply copied these out in the correct SymPy format, and then formulated the P2 Lagrange interpolation formula simply by L0 times F0, L1 times F1, L2 times F2. Then integrated this between x0 and x2. Remember that we are integrating here from x0 to x2, as x1 is an interior point. The doit will of course compute the integration, and then I've asked to factor this out, and then use the substitution command, x0 as x0 plus h, and x2 as x0 plus 2h, and then finally factor again after expanding the IP2, and you should result in this expression. h over 3, the first and the last, and 4 times the interior point. So before turning our attention back to the Gaussian integral, just to mention that if you used the SymPy, you could derive a third order, the same SymPy commands actually, you could derive this third order approximation, which requires, it's called affectionately known as the Simpson's 3/8 rule, because we've got 3/8 times h. It's the first and plus the last 3 times the internal ones. So now we're going to evaluate our work on this Gaussian function again, which we couldn't find the integral to using our primitive functions. And to do this, we're going to now apply the things that we just derived. So I'm importing both pi, square root, and exponential from SciPy or Skippy, and then I'm setting up the Gaussian function as a lambda, as the the exponential of minus v times v. The way in which Python, you can use defined functions in Python, very simple. Use the def command, name of the function, in this case new coat for Newton cotes, first order, and f and x, and unlike its compatriots, Python's quite happy to take in functions as a parameter, because it's a object-orientated programming language, and therefore we'll see functions such as this Gaussian as an object rather than just a variable or a function. So I've got a local variable here, h, which is simply where x is the limits of integration in this case. So we've had x1 minus x0 will give us h, and then very simply x0 equals x. The 0th value of x, and x1 is the first value of x. Then we just apply the formula derived, the trapezoidal formula, h times the function evaluated at x0 plus the function evaluated at x1 divided by 2. And to run this function, we simply then say new coat, present it with the function we want to evaluate and the limits of integration, in this case 1 and 2, and this provides us a value of 0.9309. Moving on to the second order integration method, the second order Newton cotes. We've defined a function here, new coat 2 f of x, and this time we've computed h, because there's 3 points, as x minus, there's 2 strips, 3 points, so it's x1 the end of the integration minus x 0, the beginning of the integration interval, divided by 2. And then x0 is put equal to the first value from the integration, the limits of integration. The interior point is calculated simply from where the first point of integration plus h, and then x2 is put at the end of the integration process, the end of the integration interval. We then ask it to return the value h over 3 function of x0 plus 4 times x1 plus the function evaluation at x2, and to run it simply the same again, but just use a new code 2 as the call, and then we put in the same, the integrand to be so the integrand, the thing that we're trying to integrate, and the limits of integration. Finally, moving on to the application of the 3/8, Simpson's 3/8 rule. Here again, rather than dividing by 2, we divide by 3, hx1 minus hx0 divided by 3. x0 is put equal to the first value, the lower value of the integral. The interior points are computed by this x0 plus h, this x0 plus 2h, and finally x3 is then computed, is found from the second level of integration, or the end of the integration interval. And then we just apply the formula. So this is 3 times h over 8 multiplied by the sum of the function evaluated at x0, 3 times the function at x1, 3 times the function at x2, and the function evaluated at x3. The call is the same apart from Newton cote being 3 to indicate that we need to be using this new function that we've put together as the third order. And this gives a value of 0.34971. And if we compute the errors given the Skippy error function, so we can find the error function within Skippy, we find that the first one is 42% in error, which one would expect. We've only used 2 points. Remarkably, the error is very, very much reduced to 0.21% for second order, and for third order it's minuscule, at 4 times 10 to the minus 7%. So the actual error being 4 times 10 to the minus 9. So perfectly adequate for the vast majority of engineering calculations is second order or third order. So just a note on the composite formula. Repeated application of these pedantic discretizations will effectively increase the number of subintervals, and this reveals what you're probably aware of, the trapezoidal rule, 1/3 Simpson's rule, and the 3/8 rule. So for the trapezoidal rule, if you just keep applying it across each subinterval, you'll find that this formula will drop out. It's the first times the last, twice the sum of the remaining, and the result of that is multiplied by h over 2. And for 1/3 Simpson's rule, or usually just drops out as Simpson's rule, in the pre-calculus mathematics, GCSE mathematics at higher level, I think Simpson's rule is there. In this case, it's the first plus the last, 4 times the odds, because this would give us an odd if you look, and twice the evens is probably the way in which you remember it. And there is a third order. So if it was done at third order, you'll find this is the 3/8 rule. So it's again the first times the last. It's 3 times these, 3 times the next, and then twice times the final interior points. If you do these in so 5 as it were. So you do 5 at a time as it were. Then you do the first, the last, and then the interior points is 3, then 3, then 2, and then multiply by 3 eighths h. And this is where the rules come from, I guess. You've got the trapezoidal rule because it basically divides it into trapezoids. The 1/3 rule, Simpson's, which is because they h over 3, and then the 3/8 rule because it's 3/8 times h. Okay. Just a note on Richardson's extrapolation. As I said, you could just increase the amount of interval, and we'll see this. And we call this brute force affectionately. Richardson proposed a method which combines two integral estimates, each with O even, to obtain a third. So this is, you'll see in a second, but this could be an order of h squared, then an order of h to the 4, and 6, to obtain a third more accurate estimate of, say, h even plus 2. So you start off with an even number, say using the trapezoidal rule, and then this would increase. You can use a formula, which we'll derive momentarily, to estimate a new integral which is of higher order. The truncation error now is whatever the order was originally plus 2. So for the trapezoidal rule, we say, well, we could set up the trapezoidal rule, or we could see the trapezoidal rule, I guess, as whatever the value the actual area that we require is equal to the area at h, at some value, some strip h, plus c, which is a constant, time h squared. Alternatively, if we evaluated it at h over 2, so we reduced h by 2, we could say this is the area of h over 2, and then of course we'd have to square both, so we get h squared over 2 squared. You've then got two equations which you can solve for c and then resubstitute in. So you will find then that a is equal to 2 squared h over the area evaluated when h was h over 2 minus h over 2 squared minus 1, and then that's plus the order 4th term. So it's actually increased the accuracy. What we've actually done is we've taken the value, a more accurate one, and you'll find there's a weighter on the more accurate one, and then taken off the less accurate one. If you then apply this, so you sort this out for this particular problem, you'll probably see you've got a 4 on the top and a 3 on the bottom, and there's always a 1 here. So we have 4 over 3 AH2, as if we calculated with, so initially, as we did before, we had 2. We start off with 2 on a linear Newton-Cotes formulae, and then we'd move up to 4 strips. So this would be calculated on 4 strips perhaps, and this would be calculated on 2 strips. And if you took out what the 4 strips was and take this weighting off, the order of accuracy now is increased to h to the 4. And of course you can do it again. Now there's a pattern to notice here. You can go through the process of doing it again, but the pattern's easy to see. 4 times 4 will give us 16. You always take 1 off, and on the bottom it's always 1 less. So we multiply by 4 each time. So 4 gets multiplied by 4 to give you 16, and then we would have 15 on the bottom, because it's 16 minus 1, and then this is always minus 1 because these should add to what's on the bottom, so it's 16 minus 1 equals 15, or alternatively you can think this value then becomes OH to the 6. And then we multiply by 4 again to get 16 on the top. 16 minus 1 gives you the 63 on the bottom. So that's the pattern, and then the next one is h to the 8th. And as we've seen, usually h to the 8 is pretty much enough for all the applications which we'll use on the module, but you could increase and increase and increase. Increasing and increasing and increasing leads to what we know as Romberg integration. So this technique attempts to optimize the number of strips required by using Richardson extrapolation to minimize the truncation error. So here we compute, if you carried on with that formulation, you could set up A as a function of 1 comma j, where j is the level, so at level 2, then it's 4, 2 to the minus 1, for instance, and then this would be I plus 1, j minus 1, I, j minus 1 on the top, and then this is of course raised to the 4 minus 1, so it's just a generalization of this formula. And where Aij is the area approximated with 2 to the minus minus 1 n intervals positioned in the Romberg array as shown. So here we have the level of integration, and here we have the number of subintervals. So what we've just described here is the Romberg integration, where we could do we could start off with n, then 2n, then 4n, for instance. We'd then compute 3 particular integrals, and then from those 3 particular integrals we could, so from these 2 particular integrals, we could work out the best approximation, put it in here, the worst approximation goes in here to obtain the next result. And likewise we could do it with, if we increase to 4, and so on through the array. Now this is quite tedious. It will render excellent results, as we'll see. However, fantastically in SciPy Integrate it's automated, and we can actually see the array, and there's hardly any work to do at all. But this is the underlying principle of Romberg integration. So moving on to a very clever method, which is used in a lot of texts. It's called Gaussian quadrature, but I like to call it Gaussian Lagrangian quadrature, as it does use principles from both of these mathematicians. This is an extremely clever method which doesn't split the intervals up equally. Instead, it uses a method where it will change the points with the interpolation, and it tries to find the integral exactly by taking away the points which is added into it. So it selects the points in a particular way where it could compute the value of the trapezoid exactly. So you can see here the value that's over approximating here, it attempts successfully to take those away by taking away these particular values which it hasn't approximated with this particular interpolation. The integral is then computed by weighted sum. So the integral is first of all mapped between minus 1 and plus 1, which is very clever, and quite simple, whereas we'll see in a second. So all integrals from a to b f of x dx can be mapped to minus 1 x. This is a change of variable. I've used cat-c here, but cat-c psi is also used in a pronunciation. It's kind of the Greek letter for x, so that's why it's used. And then we'd sum from I equals 1 to n on a weighting, which we'll find in a second, multiplied by the value of the function at a specific point, which is kind of called in the trade the Gauss points. So the integral is mapped to an integral between plus and minus 1, or minus and plus, minus 1 to plus 1 I should say, and then computed through a weighted average, and it's done in such a way that it gives you the exact result for certain interpolations. The Gauss points. These should really be called, as we'll see, the Legendre points. However, in the trade, they are called the Gauss points. First, every integral is mapped to another one between the limits of minus 1 and plus 1. So, as I said, once we have it in this form, we can then apply n from 0 to n minus 1 on 0, where the C at n is actually the Gauss points. The weightings are evaluated at the so-called Gauss points, which should really be called, as we'll see in a second, the Legendre points, such that the resulting integral is evaluated exactly. And it's straightforward, a linear line with C on this axis and the values of x going from plus 1 to minus 1 on this axis with a and b on this axis, simply evaluating this gradient would be C minus a, so anywhere up here C minus a, must equal x minus x1, the rise over the run, and likewise we could say b minus a is of course equal to this minus this. So we have the rise over the run in each case, and that is how you're able to map very simply from C to x. So this cartoon here is well worth its weight in gold if you ever do need to do the mapping. However, Python's very, very robust, written very, very well, and when we compute these integrals using the libraries, then there's no need to make this mapping. So applying this principle to a linear function renders the following. In the first instance, we need to decide how to generate equations to solve for the 2 points. So there'll be a weight at the point plus an evaluation of the function or the place in which to evaluate the function, ergo the Gauss points. And what Gauss said was, well, just assume C a standard for the integral, and then just increase this, so enough, increase the power such that enough equations are generated. So in the first instance we have C to the 0 over the limits of minus 1 to 1, and since this is the function 1, then you should see the value of 2. Alternatively, just perform the integration. If one performs the integration here, we would have C raised to the power of 1 divided by 1, and then we'd have to evaluate this new function, the antiderivative at the value of 1, and take that away from the value of the integral evaluated at minus 1. So essentially that's 1 minus minus 1, which would give us 2. And then we just apply Gauss's rule, which says it's the weight multiplied by the function evaluated the integral, the integrand, which is 1, the second weight, the function evaluated the integrand. So this is C to the 0, C1 to the 0, C2 to the 0, which in this case are both unity. So we have a very simple equation, W1 plus W2 is equal to 2. And then we move on to the next integrand when the power of C is equal to 1 between the same limits of integration. And here we would say this is W1, C1 raised to the power 1, W2, C2 raised to the power of 1. So, and again, because this is a odd function, you should be able to see that the function of cut c would go through the axis, the cut c axis, and anything on the positive side would give you a positive triangle, and everything on the negative side would give you a triangle under the x-axis, so they should cancel. And this is true of any what's known as odd functions, where this is an odd power. So it's probably one of the reasons that Gauss decided to use this convenient interval from -1 to 1. So this leads to the, since this integral is essentially 0, we have the weight at 1, and then the value at the integral, the integrand, evaluated at cut c1. So that's cut c1. And then we have w1, w2, and then cut c evaluated at this integrand, which is just simply cut c2 evaluated at this integrand raised to the power 1. Moving now to a squared term, and this time, because the values will be above the line, we expect to have a positive integral. So computing this out, again, another useful technique to use here is to say, well, I know what the coefficient of this is. This is just simply 1 over this raised by 1. So it's 1 over 3, and then I would, of course, multiply by 2 because of the range of integration. So again, that gives us, always allows us to compute the even functions using Gaussian, Gaussian's technique. And so we have w1 cut c raised to the power 2, w2 cut c2 raised to the power 2 must equal twice a third, which is 2/3. The next function is, of course, odd, so the value of this is straight away 0. You could compute this out. And then we have w1 cut c1 raised to the power of 3, w2 cut c2 raised to the power of 3 equals 0. And then there's enough equations to solve. We have 1, 2, 3, 4 equations for the weight and the value of the Gauss point at each of the points. And so the result of this analysis, that is to say solving each of these equations simultaneously, and I recommend the use of a CAS such as SymPy, will result in w1 equal to w2, which is equal to unity, and the Gauss points cut c1 and cut c2 equal to minus and plus 1 over the square root of 3. So this effectively means that the integral on any function of cut c between minus 1 and 1 is equal to the integrand evaluated at minus 1 over the square root of 3 plus the integrand of 1, the integrand evaluated at plus 1 over the square root of 3. And if there was any doubt, here's a general linear function, y equals mx plus c, and we're to integrate this between minus 1 and 1, and if you compute this out, the result is, of course, 2c, because of it being a linear function, but this being a odd function from here, and the m being, so this is just this integral plus c, so this part is of course 0 over this interval because of this rule here, and then c becomes just c on integration, and we'll get 1, so we'll get c, and then you just got to cut c, so by this particular problem the answer is 2, so the answer this time is 2c by a combination of these two rules. So there, but however, if we were just to evaluate the integral at these special points, these special Gauss points, then you'll find that m minus the square root of 1 over 3 plus c plus the function evaluated at 1 over the square root of 3 gives you exactly the same result. Moving up to cubic quadrature, what tends to happen is they don't tend to do quadratics. For some reason, in the literature they seem to use first order, then third order, then fifth order if required. And I don't really know the reason for that, but it is what it is. So the thing to also see here is that the values of 2, 0 and 2 over 3, because of the way the integral is set up, is already set up from the previous work. So we have 2, 0, 3, but in this case with the weighting would be 1 times the function evaluated at C1, the weighting at 2, the the function evaluated at C2, and the weighting at 3, the integrand evaluated at C3. So by the same logic as before, W1, W2, W3 must equal 2. The second one is of course 0, so we have W1 at C1, W2 at C2, W3 at C3 equals 0. And then the next one, again, it's just 2 over 3 because it's simply integrating a very simple polynomial. But this time the weighting is the weighting at 1 at C1 squared, weighting at 2 at C2 squared, weighting at 3 at C3 squared, etc. And we continue the pattern down. In this particular example, I've defined a function, and I'm going to solve this function using methods from the first week, which was to solve, or the first video lecture, where we solved nonlinear equations in a particular manner using the fsolve command. So in this particular case, I've put W1 equal to x0, W2 equal to x1, W3 is equal to x2 in Python script, as it were, because I'm going to then solve this function for x as a vector or a vector quantity. And so what I'm saying is the weights will be in the first 3 and the C's will be in the second 3, or the Gauss points will be in the second 3. I've then simply said return these equations. So this is W1 at C1 raised to the power of 0, W2 at C2 raised to the power of 0, W3 at C raised to the power of 0 minus 2 because we need the residual. And I've just repeated that process. So it's very simple to generate these. The only thing required actually are these each time, and then an fsolve can be used, of course, to compute the weightings. So this is a method, a rather robust method, and could actually be adopted for these to also be vector quantities, of course, in which to find the Gauss points for any order. If that's done, these are the values which are evaluated. So this is the value of each of the Gauss points. This is the value of the weights, weight 1, weight 2, weight 3, and the value of the Gauss points is minus 0.774597, 0, this is quite close to 0, and 0.7. So again, going up to the third order, we have this nice bit of symmetry, and perhaps this is why it tends to be used so much throughout the literature. So as noted previously, the Gauss point, the so-called Gauss points, occur at the roots of the Legendre polynomials required in the required range between -1 and +1. And this is why the technique should be properly named Gaussian Legendre quadrature. So a clever formula to generate the Legendre polynomials is this, which is 1 over 2 to the n factorial, the differential with respect to n on c squared minus c raised to the power of n. So for instance, if this was 1, then we would have the value, if the first order polynomial, Lagrange polynomial, is 1 over 2 to the 1 factorial, which is 1/2, and then we just differentiate the thing inside here because n is equal to 1, so this would just be 2 could C would cancel with this, the 2's would cancel with this, the 2 would cancel with the half, leaving could C. So we have the first root of the Legendre polynomial is 0. And if we went up to the second, we would put 1 over 2 squared times 2, which of course is 8, and then we differentiate this twice. So we differentiate it first, and then differentiate the whole thing first. So it'd be 2 times this multiplied by what's differentiated inside. So we would have a 4 cut C outside. So this is where the 2's are gone. We'll just remain in a half, and then we'd have to differentiate again to get 1 over half 3 cut C squared minus 1. And we then ask what are the roots of these, and this will tell us the Gauss points for the linear. It's always 1. It needs the Legendre polynomial above this, and we can see that this would be plus or minus the square root of 3. And if we can compute it out for 3, again we'd have to use the chain rule twice here. So first of all you'd multiply out by, so you differentiate here, a 3 would come down here, so one of the 3's would cancel, so therefore you'd have 2 to the 4, which is 8, and then differentiate what's inside, which would simply be 2 cut C, so that pops out, but this would be reduced by a power of 1. Then you could differentiate again. In this particular case, I think I multiplied out, collected terms, etc., and then eventually end up at this point. And you can see here that one of the roots is at 0, which is what we found for the third, and then we have another couple of roots at plus and minus the square root of 3 over 5, and that would be if we used a 4th order, and then we could go up to 5th order, etc. The next one looks like a job for SimPy. So if deemed necessary, then SimPy or indeed Maxima can be used to generate the iterative evaluations of the Legendre polynomials. So here we've set up from SimPy, we've asked for symbols and a capital S symbol, and this is so we can invoke n to be an integer. As with all Python objects, they can be subjected to lambda calculus, and therefore p equals lambda passing through now the symbolic objects n and cut c to compute the differentiation for us. We can then from SimPy import, expand and factorize, and in fact the only thing that's required in this particular case was factor. We had p5, and this would have generated the 5th order polynomial. It's always worth verifying these in Maxima. It's an even simpler in Maxima as it's a cast by default, and it has nice little things like n factorial. The raised to the power here could be used. The double multiply will also work in Maxima, and again factor p factor 7 using this function would generate this polynomial. And taking the roots of each of these polynomials will produce the Gauss points as just calculated.